I'm Alexander Zhang. I'm a software developer at Topaz Labs, which is what could be described as an image quality company. Um, uh, Gigapixel is the product of ours I've worked on the most. It's a desktop app that lets people with no knowledge of AI or programming use super sampling models to enlarge, say, old photos to the size needed for a poster. A critical part of accomplishing our goals is to fit into an existing workflow. And that means apps and plugins that run on the user's desktop or laptop. And it means getting the performance users expect out of whatever hardware they have without manual configuration, and keeping up with advances in the state of the art by delivering the latest and highest quality image models available at any given time. Desktop is a somewhat less common deployment scenario with many of its own challenges. It allows users to edit offline and not worry about internet speed or privacy policies. But when compared to a server deployment, there's a lot less control for us over the system. Restrictions on the GPU or operating system have to be carefully considered, and while we can provide a set of system requirements, it has to be reasonably broad and easy for users to check. There's also more diversity in desktop GPUs than even most mobile or embedded deployments, and users expect not only to be able to run everything with more than 5-year-old cards and drivers, but also for the performance to scale well on the latest hardware. There's also usually other applications running, like photo editing software, which can put memory or responsiveness constraints on our app. Our solution here is to rely on different inference libraries for each of the hardware vendors we support. OpenVINO on Intel, TensorRT on NVIDIA, DirectML by ONNX runtime on AMD, and CoreML on Mac. That means we need a way to specify the same model to many different libraries, and that's exactly what we use ONNX for. After training models in TensorFlow or PyTorch, we convert each through ONNX to create a specification of the model architecture that can be used by each of the different inference libraries. That way, we can provide a relatively consistent result on different hardware while saving a great deal of manual work on each model. Without ONNX, we wouldn't be able to support so many new models on so many GPUs, but there are still challenges associated with any conversion. One is ambiguity in the specification. One example is that in many of our older models, we found that in some libraries, the output of the model was shifted by a pixel, and on some, the result was blurrier than on others. It turned out that those models included bilinear resize operations, and when they were converted using ONNX offset 9, I believe, the alignment of the resize was not specified, and this led to different backends implementing it differently. Some use the same rather unique input and output pixel alignment as TensorFlow 1.0's default, but others align the corners as would be most common elsewhere, or shifted by half a pixel, causing different results. In this case, we were able to change to a newer offset, which has more parameters for its resize operator and get more consistent quality, but ambiguity is still something we have to look for and test every time. There's also the issue that libraries aren't uniform in what they support, and even where they are, getting the best performance may mean adapting the format of the input or changing up the pre- and post-processing operations. Some degree of inconsistency is inevitable when using different sets of fused operations or intermediate accuracy, but it's not necessarily easy to quantify what's acceptable to users. And finally, performing and troubleshooting all the library-specific conversions may require getting your model to a lot of different machines just during development. So to address these, we try to avoid compatibility issues by performing test conversions before training a model. That helps avoid surprises and can give us some information about the performance. To make the most of each library's capabilities, we usually have to create a different ONNX representation for each before conversion. And this does sacrifice some of the benefits of a uniform format, but it's still faster than respecifying the network from scratch. And for quality discrepancies, using the latest ONNX offsets, explicitly specifying as many parameters as possible, and avoiding troublesome operations like bilinear resize if necessary, have been pretty useful. We still need to be sure of the results, though, so there's no good way around visually comparing the results of each conversion But while that can be a lot of work, some tools to compute similarity scores numerically and generate side-by-side test images have been helpful. As for the hardware requirements, we've set up a CI pipeline to run conversion scripts, but while it's not very capable or quick to use yet, it's already saving a lot of time running around between computers. You may be wondering why we do so many conversions ourselves rather than using one or two different libraries like OpenGL or DirectML Everywhere, or using an existing universal wrapper like ONNX Runtime Everywhere. One reason is performance. Newly introduced hardware especially is naturally best supported by their own vendors often, and not using their interface means you can see less of a performance improvement or see it later. Using a more generic interface will also usually mean additional conversion costs or loading steps, and that can make a big difference for our apps, where users often want to compare multiple models or chain them on the same image, even though they likely don't have enough RAM to store multiple models on the GPU. Related to that is flexibility to optimize for our own models and performance needs if desired, without being obligated to write lots of model-specific code for every model, like you might with OpenGL. Getting consistent quality and speed from desktops isn't just a conversion time issue. There's also a lot of tasks in the runtime inference pipeline that we must do besides just calling a library. We need to determine which models can actually run on the user system and select the appropriate configuration, things like numerical precision, input format, and inference device. For our use, it also needs to handle running arbitrary size images through a model, despite variation in each user's and library's maximum input and output sizes, and present a uniform interface despite different setup, loading, and pre- and post-processing steps. To address compatibility and selection without having to actually test every library at runtime, which would be slow and lead to unpredictable crashes for some libraries, at the time of conversion, we also write a JSON file describing the system requirements, memory usage, input names, and other library-specific details for each variation of a model. This can be matched against system information found at runtime to determine compatibility. Selection is based on preferring the discrete GPU with the most VRAM and using the library with the most specific requirements compatible with it. This doesn't guarantee the best speed, but works well in 99% of cases. To handle arbitrary input, we split images into blocks, select an appropriate size based on VRAM, and then run the blocks through inference. This allows us to maximize throughput through batching and potentially run on multiple devices and libraries in parallel. In the future, some concerns are how to fit larger models onto consumer GPUs despite lower VRAM availability, and the perhaps related problem of how to change between different models quickly when chaining or performing comparisons. There's also continuing difficulty in ensuring new model architectures can be added and behave well across all libraries. The fact that we use more than one means it can take a lot of work and time for some newly introduced layer type or operator to be implemented in all of them and the bugs ironed out. The result of all the conversion work can be difficult to handle with hundreds of files for different models and configurations. It can be easy to miss one with the wrong permissions or a quality issue, and just moving them around takes a long time. We are hopeful, though, that the general strategy we've taken so far will be up for these challenges and enable us to frequently deliver consistent image quality improvements to get the best speed out of all kinds of desktop systems. And thank you for listening.